So this is part 2 of our video series with 7th grade math standards. So we're going to pick up with task 8, and we're looking at our standard 7G3. And this is where we're starting to look at if we have cylinders. Notice what we're talking about, a cylinder. So what would happen if we slice it horizontally? So what you're thinking about is when you slice that left to right with the cylinder standing upright, what do you see if you took the top off of it? Okay. Well, you should see a circle. What would happen if you take the same cylinder and you slice it vertically? Well, you're going to see a rectangle. If you take a cylinder and you slice it diagonally, then you would see an ellipse. Now, that's kind of an advanced vocabulary word for the kids at this point. They're not going to talk about an ellipse, but it's something you could certainly show them. They could Google. There is a video that I'm going to upload in your module in regard to supporting videos. So it will be labeled, when we look at cross sections of 3D figures, look for the video that's in this module for week 5. So this will be something good to check that video to where you can see the different cross sections. Now, that was a cylinder. So let's look at what if we have a rectangular prism. And a lot of times it's how you draw it. So if I'm looking at the rectangular prism upright, and I slice it horizontally, well, especially if this endpoint is a square, then what I'm going to see is a square. Now, if it's not, then it would be a rectangle. And if I take the same rectangular prism and think about slicing it vertically, you would still see a rectangle. And think about if you sliced it diagonally or in a different way, and you sliced it, let's say, diagonally this way, think about what shape you're going to see when you open that up, and you would see a parallelogram or a rectangle, depending on, those can vary. The different shapes can vary, but we're definitely focusing on the horizontal and the vertical 3-dimensional slice for different shapes. That's where the big focus is for the students. All right, and then if you take a triangular prism and so when you take this type of shape and think about if you slice it, if you slice it vertically, then I'll take another color here. If you slice it vertically, then you're looking at slicing it up and down, and that's where you're going to see your vertical would be your triangle. Now, if you take that same shape and you slice it horizontally across and open it up, well, then you would see a rectangle. It's a really good activity for the students is to use Play-Doh or clay, because this is something where they can take maybe fishing line or floss or plastic knives. And I know you think plastic knife in class, but that would be something that they could definitely use to cut the Play-Doh. Or you might want to stay with maybe some string, and students can work in pairs. One can hold it, the other one can kind of slice it with that fishing line. That just gives you that nice cut where the kids can then open it up and they can see what shape they're dealing with. Now that's just the physical part of that, if that's something that you want to do in class. We also have any type of interactive or visuals through links, and the internet has good links that I'll provide for you that you could share as well for the kids to be able to see it and what that looks like when we're talking about a horizontal slice and a vertical slice. And then we can slice it differently, and different shapes can come up. We can see rectangles when we take this triangular prism, and if we sliced it along the sides here, we would see that rectangle piece. So that's just a different view. Again, we've got a rectangular pyramid. So this would be either a square pyramid or rectangular pyramid, whichever one, but pyramids are named for their base, and they meet at a point. So when they meet at a point, you're looking at the base. And if the base is a rectangle, then that's how it's going to be described. So think about that. And then what would happen if we cut it horizontally and open that up? What would we see? Well, a horizontal cut on a rectangular pyramid, we would see a rectangle. A vertical cross section, so that means we're just cutting it right down at the peak, we would see a triangle. And then we can take that same if we cut it at a different angle, then what we would see is a trapezoid. So we've got a triangle as the vertical cut, we would have a trapezoid. I know it's hard for me to really show that just through my drawing a line that's horizontal or a line that's vertical, but the video link is really helpful for you to see what I'm talking about with that. When you're talking about a cone, think about cutting a cone horizontally. You're just looking at what you cut. So you're looking at what lies inside, or if you take the piece you cut out or cut off and you look at the shape that you see in your hand after the cut, well, that would be a circle. And it would be different if we cut it vertically, then we would see a triangle. And then a different type of slice, and this is the neat one that students they won't see for a while, and that is when you take a cone and you cut it at different sections, you're creating different figures like your parabola or a circle or an ellipse or a hyperbola. And now you're getting into your conic sections that you deal mostly in, doesn't come back until pre-calculus for most kids. So these are really your conic sections. Notice the root word there, we're dealing with cones. So when you take different slices at different angles, you create different shapes. And then, of course, if you have your sphere, And so when you have your sphere and you cut it at any angle, vertically or horizontally, you're dealing with a circle. Spheres will come into play in 8th grade, as well as the cone. But this allows, they're not doing any work with volume or surface area or anything like that. It's just more what type of shapes are created when you make a horizontal cut or a vertical cut on a 3D figure. (7G4). So we're going to be looking at cylinders. We're going to be looking at circumference, diameter, and area. So when you take any type of circular object, so if you measure that distance around the cylinder, then you're creating circumference. And then if you measure the diameter of that cylinder, those two measurements circumference divided by the diameter will give you something that's approximately close, that's near the pi value. And we approximate pi as 3 14/100ths. That is not the exact value because it's irrational. We cannot put an n to the decimal. So we cut it off at usually 3 14/100ths so we can work with it and get an approximation answer. So when we're looking at determining the relationship between the circumference and the diameter, we're looking at formulas, okay? So formula 1 would be the circumference is equal to pi multiplied by the diameter. And then formula 2 is replacing the diameter with twice the radius, because that's what you have. You've got a radius here, and you've got a radius here. So r plus r gives you the 2r, which is equivalent to the diameter. Here's another video that I will post, and that is proving the formula for a circle and why it is area equals pi r squared. And it's very interesting. And the activity that goes along with this that you'll find in your student handout allows the students to work at different sections. So if a student cut a circle into four sections, well, then what you're kind of creating is only 4 pieces to the circle. So when you cut those out and put them and arrange them, what you're noticing is that you are creating a parallelogram. And so the more pieces that you can cut the circle into, you will notice from the video, the more and more it gets closer and closer and closer to your parallelogram, closer and closer to a rectangle where we know the height. And what we'll see is the pieces of the circle positioned carefully. And so what we'll find here is this is all of the outer parts of the circumference. This will make more sense when you watch the video that I'll upload in the module. But what we have here is half of the circumference. So here is 1/2 of the circumference, and here's the other half of the circumference. And what the height is, actually, the height is the radius, because you're looking at the height of each of these pieces is actually r. That's your radius of your circle. Well, here's what we know. We know that area is equal, of this that we're looking at, area is equal to r multiplied. So the base, which is 1/2 c, times the height, which is r. So here's what we have as our area. Now, what does circumference equal? Well, circumference, remember, is equal to 2r times pi, or pi times d, the diameter. Well, we're going to use this one because we're already in terms of r here. So we're going to substitute here, and so we're going to have r multiplied by 1/2 r times pi. And notice I also have the 2r, which I didn't. I'm going to start over with that. So area equals r, which is what I had right here. And then 1/2 times the circumference. Well, here's my circumference. So this is going to take the place of c. So I'm going to have 1/2 multiplied by 2r times pi. And when I multiply all this out, the 1/2 and the 2 will multiply to go to 1, and then r times r is r squared times pi, which gives you your formula for your area of a circle, which is pi times the radius squared. So that was probably a sloppy version of that proof, but when you see the video, you're going to see it'll break it down much better than the way I did in this on this page here. But that's the idea, is where the pi r squared is coming from. All right, so knowing that formula, I want to calculate the area of the figure below. Well, we've got 3 pieces actually. We know we have a rectangle. So the rectangle is going to be, we know this is 6. So we know that length is 6. So we know this length is 6. Well, it's 14 all the way across the base. So 14 minus 6 is 8. So where can we evenly distribute 8? So that's going to be 4, and that's going to be 4. So what we actually have is, if this is 4, then we know this is 4. So 4 is our radius. All right, so the rectangle is going to be a 6 by 4. And that's going to be 24, and we're dealing with inches, so that'll be 24 square inches as the rectangle. Now, the area of a circle, remember, is pi r squared. Well, we don't have a full circle. Matter of fact, we have 2 quarters, and 2 quarters would make up half of the circle. So we've got half of pi times the radius squared. Well, we know the radius is 4, because that's what we found, the radius to be 4. So what we're going to have is simplifying this equation. So let's do our exponents first. So 4 squared is 16. So we're going to have 1/2 times pi times 16, and then half of 16. That would give us 8 pi as the area of the 2 circles, plus 24, and all of this is going to be in square inches. So the area of this shape that we don't really have a name for, it's kind of like maybe If you're looking at the area of a track and field, it would be half of it. But we had to kind of piece together formulas that we know, which was the area of a rectangle and the area of 2/4. If you put the 2/4 together, then you're going to have half of a circle. So the 24 plus the 8 pi is all in square inches. So that would be your exact answer. Notice that's your exact answer because I left it in pi. Now, if we wanted to do an approximation, we could say 8 multiplied by 3 14/100ths, which would give us 25 12/100ths plus 24. So that'd be what, 49? 49 12/100ths square inches, and that would be an approximation. Next problem. We know that we have a square with an interesting shape that is inscribed within the square. So this is a 14 by 14 square. So the area of the square would be 14 by 14 or 196, and this is inches, so it would be square inches. Don't forget your units. Now, I want to know the exact area of the shaded region. So if we're using approximation, we can use 3 14/100ths. If we're looking for an exact, we can use pi. So what I need to find is I need to be able to find the area here and subtract it away from 196 square inches. And that's going to give me the area in green. All right, so what do we know? Well, we know that if this side is 14, then we know that the radius is 7. And since the radius is 7, we know that area equals pi times the radius squared. But this would be 1/4, 1/4, 1/4, 1/4. So we have one whole circle. So that would be 49 pi. That's the area of what's in yellow. So what we would take is the total area minus the area in yellow to get us the green area. So that's going to be 196 take away 49 pi, which would give us that exact value. Now, if we want to get an approximation, 49 multiplied by 3 14/100ths is approximately, notice my symbol, approximately 153 86/100ths. So if we take 196 and take away 153 86/100ths, we're going to have an approximate value of 42 14/100ths square inches. And that would be your area in green. Okay, next practice here is I want to calculate the area that's shaded. But for one, I want to calculate the entire area in terms of pi. So 1a, if the diameter is 12, then we know the radius is 6. So the diameter is 12 centimeters. The radius is 6 centimeters. So the area of the entire circle would be 6 squared multiplied by pi, or 36 pi. So that's the entire area for 1a in terms of pi. That's what that means, in terms of pi. That means we have pi in our answer. So 1b says calculate the area of the shaded region in terms of pi. Well, remember that the shaded region is actually a fourth of pi r squared. It's a fourth of the entire circle. And we know that the entire circle is 36 pi. So 1/4 of 36 pi, that area is going to equal 9 pi. And it's 9 pi centimeters squared. And this was 36 pi centimeters squared. And then C says calculate the circumference in terms of pi. Well, the circumference, remember, is diameter times pi, or circumference equals 2 times the radius times pi. So it's whatever you want to use. You want to use the diameter, or you want to use 12, or you want to use 6. It doesn't matter. If they use 12, then it would be 12 pi inches, or sorry, centimeters. It's a linear measurement. It's not squared. Area, square units. Circumference, perimeter, linear units, where the exponent's 1. Area, square units, the exponent's 2. When we deal with volume, the exponent's 3. Here we want to calculate the entire area, and we know the diameter is 16. So for 2A, we know the diameter is 16 centimeters, so the radius is 8 centimeters. So area equals pi times the radius squared. So area would be 64 pi in terms of pi, 64 pi square centimeters. That's 2A. And then 2B is, I want to know the area of the shaded region. Well, that is 3/8 of the 64 pi centimeter squared. So I really only want those 3, and it's not the entire figure, it's 3/8 of it. So that area would be 3 times 64 divided by 8, so that's 24 pi square centimeters for 2A. And 2C says find the circumference. Well, again, that is circumference equals the diameter times pi. I'm going to use diameter. So that would be 16 pi centimeters. Next, we're going to look at 7G5. So we're looking at using this supplementary angle idea that we've already talked about in video part 1. But now we're going to use it and make equations knowing that this measure is equal to 180. So what we have is I want to know angle BOA and I want to know angle COB. Well, right now I know that BOA is 2x minus 15, but when I add that to 11x, I'm going to get 180. So I'm solving equations here. The 2x and the 11x are like terms, so that's 13x minus 15 is equal to 180. Inverse operations, I'm going to add 15 to both sides. So I get 13x is equal to 195. Inverse operation, I need to divide by 13 because I'm multiplying 13 by x, so I've got to do the inverse. And when you do that, you're going to get x equal 15. Well, that's what x equals. That's not the angle measurement. So you would take 15 degrees and substitute it. So what's 2 times 15? That's 30. 30 minus 15, it just happens to be 15 as our answer. And then if we take here, we'd have to take 15 by 11, and that would be 165. Well, remember, 165 plus 15, 165 and 10 is 175 plus 5. There's your 180. It does check to be 180 degrees. And so we've got some examples here where we know things that are 180. We see the 90-degree angle, so we know that we've got complementary angles in here as well. So if I want to find the measure of angle COE, so COE, I'm looking for that measurement, which is X right now. I also want to find angle BOF, and I also want to find angle DOB. All right, so let's start with what we know. Well, we know this entire angle is 134. And we also know that we have a 90-degree angle, and we have an X angle, and we have a 14-degree. So we know we've got 14 plus X plus 90, and all that's going to equal 134 degrees. So X plus 104. So if I take 104 and subtract it from both sides, I'm going to get X is equal to 30. So the measure of angle COE is 30 degrees. All right. COE, I know this is 30. And I also know that if you look at angle AOC and DOB, that they would be vertical angles, so that would also be 14 degrees. So the only thing I'm missing is Y. So I can look at a straight angle here, and that would be to find DOF. I know I've got 14 plus 30 plus the 90 plus the Y is equal to 180 degrees. So 14 plus 30 plus 90 plus Y is equal to 180. So this is what? 44 plus 90 plus Y is equal to 180. And so this is 134 plus Y is equal to 180. So Y would be 180 minus 134 would be 46 degrees. And so you're just trying to find angles that will complete that 180 straight angle. And so first off, we started, just to back up there, we knew that all three of those equaled 134. That's what we did here. So we did the 14 plus X plus 90. We knew it was 90 because that angle measure right there showed that it was 90. So we knew 14 plus X plus 90 equaled 130. And then once we found X, we were able to use 14 plus X plus 90 plus Y is equal to 180 to figure out the Y value. So angle BAC is what we're looking for. That's 1. And so we know that this is 90, so we know this is 90. So we know that 30 plus something, well, we know that this has to be 60 to make that 90 degrees. So if I'm looking, here's what else I can do. I know this is going to be 60 to create that complementary angle. So if you look here, you can look at all three of those angles. So that would be 5x plus 3x plus 60 is equal to that 180 degrees, which is right here. And so that would be 8x plus 60 equals 180. Subtract the 60. I get 8x is equal to 120. And when you divide that, x is going to be 15. Well, that's not what the angle measure is. That's just what you would substitute and multiply by 5 and multiply by 3. So 15 times 5, so we know that's going to be 75 degrees, and that's going to be 45 degrees. And so we can kind of fill in the rest. We know the vertical angles, that would be 60. And then we can continue to figure out, well, BAC would be 75 degrees. BAH would be 45. CAE would be 60. DAH would be 60. BAF would be 135. So BAF is 30 plus 60 plus 45. And then FAE would be 90. So we can use what we know to kind of fill in and finish that off. So some examples here, we're looking at supplementary angles. So remember, supplementary angles are just angles that are going to add to give you 180. So these three would be examples of that. Complementary angles would be these two because they add to give you that 90 degrees. Vertical angles, so we would look at these two would be vertical, and these two would be vertical, and these two would be vertical. And then remember, adjacent angles are just angles that are next to one another. So this and this would be adjacent. These two would be adjacent. Any two numbers that share the same vertex. And then final, the last two I want to look at is finding the volume and surface area of some different shapes. So surface area, I'll start with surface area, and you're just trying to figure out, well, let's find the area here, and let's find the area. If we find the area of one, we can double it to find both of those. And so we're looking for these two. And then we know that we need to find this side. And then we know we need to find the front side. But then there's also a back side as well. Okay, so we're trying to find that triangular prism is going to have 5 sides to it. So let's look at the triangle. Okay, so we know this is 8, so we know this is 8. And if we know this is 15, we know this is 15. So what we can do is take 15 times 8, because that's the base times the height, and we want to divide it by 2, but we want 2 of them. And then what are we going to add? Well, we're going to add then this side over here, which is an 8 by 20. So that's a length times a width. Well, that's going to be 160 square feet. And this is going to be 120 square feet. And then we want to keep adding. So we've got the back side here. The back side would be a 17 by 20. And that's going to be 340 square feet. And then we've got the front side here, which would be 15 by 20. and that's going to be 300 square feet. So we're just going to add all those up. When you add all those up, you should get 920 square feet. So that would be your surface area. Now, I'm going to go to another page. But if you wanted to find the volume, then what you're going to look for is the area of the triangle. And remember, that area of the triangle, we're looking at a 15 by 8. We're looking at a 15 by 8, which is what we did up here to find that surface area. So when you're finding the volume, you're going to do the area of that triangle, but you also got to bring in the height of it. So the volume of this would be 15 by 8. So length times width, but divided by 2. And then the height of the triangle was 20. Remember, the height there was 20. So when we go ahead and simplify this, we're going to get 15 times 8, and then divide that by 2, and then multiply by 20. We should get 1,200 cubic feet. Why is it cubic? Remember, because it is volume. So 15 times 8 is 120, divided by 2 is 60, multiply it by 20, and we get 1,200 cubic feet as the volume of the triangular prism, and 920 square feet as the surface area. All right, the last one. So we're thinking about surface area is going to be a little lengthy because we've got several pieces that we're looking at, okay? So remember, surface area, we're looking at all the front, the sides, the top, top, bottom, sides. We're looking at everything. So this top piece should be a 10 by 5, and I'm just going to cut it into sections. Well, if we look at this, remember, we're dealing with a 10 by 5, but we've got 2 of them. So that's going to be 100 square feet. So 10 times 5 is 50, but I need the bottom half of it as well. And then this would be 4 by 5. We rewrite that. That's 5. And we know that this is 5. And this is 5. We know that this is 4. So this is what we're looking at next, is this right here. So that would be 4 by 5, and there would be 2 of those. So that would be 40 square feet. Now we've taken care of the top parts, okay? So now we're going to come in and look at the different sides. So this is a 1 by 4. And this is a 1 by 5. And here's another 1 by 5. So we're going to have a 5 by 1, but 2 of them. So that's 10 square feet. We're going to have a 4 by 1, only 1 of those. And then over here, since this is 4 and this is 10. The difference in that is 6. So we know this is 3 and this is 3. And that height is 1. So we've got a 3 by 1, but we have 2 of them. And so that would be 6 square feet. So we've got the top, the back side of it. We've got this one, which is the 1 by 4. We've got this one, which is a 5 by 1, and there's 2 of them. We've got these were 3 by 1s, and we had 2 of those. And then we've got the back side over here. So that's also a 5 by 1. And we've got 2 of those because we'd have to look at this side as well. So that would be 10 square feet. And then we also have one more. So just kind of go through and look at what we've counted. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, and then we've got the other half as well, the back side of it. But then we don't have this very back piece, which is going to be a 10 by 1. So we should be able to add up all those pieces, and we should get 180. So 40, 50, 60, 70, 80 plus 100. So we get 180 square feet as our surface area. So the key to this one is just kind of going through and marking each of the pieces that you've, I labeled them all over here. I labeled them by the length and the width, and then there might be 2 of them. So I designated that there would be 2 of those. And so I've got 2, 4, 6, 8, 10, 11. There's 12 sides. And that's should add up to be 12. So there's 12 of those different pieces. So that's the surface area. Now when you're talking about the volume, we've got 2 volumes we can look at. So we can split it up. We can split it up right here. And so we have a 5 by 10 by 1. So I'm going to come over here. And so that volume would be 5 by 10 by 1 for volume 1. This would be volume 2. So volume 1 would be our 50 cubic feet. Volume 2 would be 4 by 5 by 1. And so that would be 20 cubic feet. And so we would just need to add the 2 volumes together to get the total volume, which would be 70 cubic feet. So we just broke up that piece into different volumes, thinking of the length, width, and the height. And so that will conclude part 2 of this series, but I also want you to be looking in the module for additional websites that will go along with the cross sections and the volume, or proving the area of a circle.